Yeah, so I think that this session maybe like maybe you will help because you probably do most of this part, but like the goal for this session was more to talk about like the memory model of the machine and everything related to the lookup and stuff. So a lot of very interesting discussion. So as I just mentioned, like the goal of course is to prove the aggregation of signature, but also to merge some previous aggregation, because when you have like you have to imagine like a network of nodes, and some nodes are responsible for aggregating like a bunch of signature, and others could be responsible for merging those proofs, and at the end we will post a single proof on chain. The memory is read-only. We had like a long debate because originally like you had some VM using read-only, some other using read-write memory, but we thought that for our use case, which is like quite a reasonable program, this is maybe more tractable to have like a read-only memory and not a read-write memory. That should be maybe better for proving Ethereum block or a very large program, but for our restricted program, probably this is better. This has also like the advantage to be cheaper to prove, and so as the prover cannot override a memory, then we simplify the lookup work and avoid more complex techniques. But like, yeah, the main challenge there is how do we efficiently prove that the prover memory operations are valid and consistent. So we have to prove that the same memory address must always return the same value. That means that if an access AV is inconsistent with another access AV prime, V should never be not equal to V prime. And also the continuity, so all set of all access memory address form a complete continuous range, and so it should enforce directly this, and yeah, to enforce this we use lookup. So lookup is a way like to enforce like a memory consistency between different tables. So if you imagine that in a very simple way, and you should be familiar with that, you should prove that there is a link between the tables in some sort, and so you have different methods of that. The most common is to run like a grand product. The grand product is using a product basically, because like you have a multiset. The multiset is the value that you can have on one side on the main trace. Like, yeah.
Why do you need the second property, security property, the contiguous?
I think that this is because at the end, like, I don't know if you agree, but we should have like a continuous after the first pass.
I think in K-row they need continuity to prove read-only, because it's the way. I think they are like an R, and there are all the memory accesses, and to make it work, they need to have a continuous memory. But I believe in our case,
yeah,
we don't really need this continuity, even though to be as close as possible as a continuous memory is good for performance.
Yeah, that was my question. Like, if
I know. It's to simplify the constraints. Like when you have like things like the memory slot one after another one, like you can do you can subtract the addresses and check if they are one, and that's simplifies a little bit the constraints of the memory.
Yeah, I think it's somewhat related to the question that you had this morning during the first pass when you go over this. Is it possible like to add more checks and to make the memory continuous in order to simplify the work that we have to be done there, or is it something that we don't?
Actually, I think in K-row they did it because what they do is that they reorder the memory, and there is an R that asserts that once reordered, you can either have, so there is like index value, and once reordered, there is a constraint that says that the index should be non-decreasing, and that's why they need it. But in our case, I don't think it would speed up because it's like the lookup argument is quite different from in Kero. So
Okay.
because in Kero, what they do is that they use I think a run product to prove that the index, the accesses during the execution are the reordering of something else, for which to prove that it's read-only, they need continuity. And so in the end, they only use a ground product argument, where they have sorted the indexes, and they need the continuity because when it's sorted, to have like an error constraint to that it's sorted, it's easy if it's simply non-decreasing without any gaps between the indexes.
Okay.
But in our case, I think we can make it work without continuity. And I'm not aware of speed up that we could gain with continuity. I'm not 100% sure,
But the continuity, I think, is used to enforce easily the read-only property.
Yeah.
Because if the addresses match, then the values should be the same. And then the problem is if you have like a variable gap, it's like impossible to ensure that
the difference is no longer one, so the multiplication in the constraint doesn't make any sense.
You need to like check the ordering relation in a harder way.
Yeah, you would have to put like a constraint that something is different from 0, which is like way harder to.
you need to introduce undefined possibility.
You can do it. We did it in Valida. It's just would be cheaper to check that ordering by address if you have this property.
But it's because in Kero they use a permutation check, while currently in the implementation in the end they use the ground product argument, and currently we use a lookup argument, but it's a bit different, I would say. And that's why we don't need this continuity.
But you like it anyway because your memory argument makes you pay for the gaps.
Obviously, we need it for performance, but if there is one little gap, it's not that bad. But yes, performance.
Okay, so yeah, thank you for the question. And so, yeah, the core idea, like to verify this corresponding multiset, could be, for example, to run like a product where like you have the roots and then you have a random element that is alpha there, and we have like an initial boundary constraint, let us say, and then we update the rule line after line in the trace, and we just check that the final constraint is 1, so that we have run all of our product and we know that there is consistency between the different tables. And if the running product is 1, this means that all of the terms in the numerator cancel out with the term on the denominator, and so you have true this. But this structure is quite rigid, and this brings you with a product to run on each of your line, and so this can be quite costly. So there is another model. Also, there is a problem, but because if you are in this condition and there is a multiplicity, that means like some values that are used multiple times into one of the traits, then you have like this exponent, and then you cannot transform that this way. So what you can do there?
Can I just go back slightly? So
yeah.
So what are we trying to prove? So we say that you have the memory trace that satisfies these two properties, and your raw unsorted. What is the raw unsorted memory trace here that we're trying to what are the two sets we're trying to show are equal?
There are multiple lookups. For instance, there is a lookup from the execution table into the memory. And there will also be a lookup from the Poseidon tables into the memory.
Okay, I see. So okay. I see. So you're trying to show that your execution tables align to what's in there.
Exactly. Because in the execution, you will have something like an index column
Yeah.
and a value column. You want to ensure that if the index is 3, the value corresponds to the memory at index 3.
Yeah. Yeah.
So it's like an indexed lookup from the execution table into the memory.
I see. So you only need these lookups then for those additional opcodes you've added, right? Like for the Poseidon 2 and some of these data
You
fields.
also need it for the add and null opcodes, because when you add and null, you access data in memory. So if you want to say memory at index fp plus 3
Yep.
plus memory fp plus 7 equal memory fp plus 20, you have 3 memory accesses. So one instruction leads to 3 memory accesses.
But isn't the point of, like isn't the reason we're writing this VM that the VMs can be easy to prove, right? Like we
Yes.
can, but like so proving like can't you just commit to your memory as a trace and then like proving addition is just like a constraint you've added?
I think this relates to the point of a circuit builder things, no? Because you can build that with a circuit builder a little bit like done in the Blanky 3 recursion project and avoid all of the work with the compiler and stuff. This is what you are saying?
I don't know, possibly. I guess I'm just trying to understand like I thought the whole point of the add and mul operations was they were like really easy to prove, right?
Actually, they are easy to prove.
So then why do they need to look like don't they not need to look up? Like aren't you just proving that the addition is correct?
But yes, but you need to look up because you need to fetch the data which is in memory at index fp plus 3, which with the certain value of fp. So you need to access this data.
No, that's not how proofs work, right? Like you commit to a trace,
Yeah.
and then the addition turn and then you have then you do some sort of general mumbo jumbo, and then you at some point check that like everything agrees on some extension field element sample.
Could I like draw a picture to
Sure.
try to explain this? So,
Yeah, I think I'm just a bit lost on what the goal here is.
alright, so we have like, let's say, a bunch of operations, and I'm gonna assign them numbers, the clock values, right? This is the first thing that happens, and so forth. So you know, let's just deal with you know, one column of operands because that suffices for the purposes of this explanation. You know, like let's say here I'm just going to write address here. This is the address that my operation is working on here, right? And maybe different operations that are distributed in time will access the same address. And then when that's the case, I care that they're the same value, right? So this is not okay, right? Because the value at address 5 should be the same in all instances. So in order to check that, I want like a memory table where I'm going to have address, value. This may not be exactly how it works in leanVM, but if so, then I can be corrected. So let's say you know, at clock 0, I've accessed address 5, and it had value 1, and you know, at clock 2, I've accessed 5 and got value 3. Now what's different here in mem versus here in the execution trace, let's say, is that mem is sorting everything by address. So like, you know, right before, right, so we've got 4, 5, 6. Whereas over here it's sorted by clock, here it's sorted by address. So now, the constraint that was not easily checked over here, that these are supposed to be the same, that's easily checked over here because these two rows are now next to each other. So we've turned a non-local constraint into a local constraint. And now the purpose of the permutation argument is to ensure that what's happening over here, all this stuff, corresponds with all of this stuff. Does that clear it up?
Thank you.
Yeah, I think it helps. Thanks.
And I think this is very similar to Cairo, where you have memory access in the execution table, and you reorder the same memory access in another place, and then where you can enforce the fact that it's read-only, and after there is a limitation argument to prove that it's the same multiset, like set.
I think one thing I don't really understand yet is that in your approach, you've got the program counter and the frame pointer in the memory as well as values at the beginning of the frame, right?
The array registers, I think.
It's not really memory, it's apart. It's two registers apart, different from memory, but sometimes you need to write them in memory. In particular, when you want to call a function, you need to write them at the beginning of the new frame of the function, in order for this function to be able to come back at your previous frame.
Yeah, okay.
But actually, it's quite separated from memory.
But would you say that like the main function has got, like we could also say that like the main function has got 0, 0 at the beginning, and then every time I call, I start like with a program counter.
The issue is that those values, FP and PC, are accessed at every cycle, and so you don't want. So it makes sense to have dedicated columns in your R for PC and FP. If you store them in memory, you need to look up them at every cycles multiple times. So it would be possible, I think, but it's more costly. And when there is value that is accessed absolutely every cycle, I think it makes sense to store it in a dedicated column, if it answers your question.
Yeah, I think, I guess my question is like when I have like a function call, I also do, like I've got a different lookup argument for the PC and FP.
Just to be clear, actually, this is like something similar to Cairo, but in the current implementation, it's not exactly implemented like this. Just to be clear, it's a little bit different.
Can you explain the differences?
Yes, explain. Because this is based on the permutation, like a grand product permutation check, and this works. Cairo does it works. Because permutation checks the equality between two sets, and lookups checks the inclusion between two sets, and what you use is actually precisely an indexed lookup.
You want to present like lookup?
Okay, but just
Yeah, you can. After like I have the lines with the lookup star, so
okay.
could be easier for you.
Yeah, so the picture I drew, that works for read-write memory, but if
Yes,
it's read-only, then we can simplify the picture a bit.
So the grand product is to check equality between two sets. Lookup is to check inclusion. For instance, you have a column A, and you want to check that all the values in your column A, all the values in your column A appear in another column B. 7, 8, 1, 2, and you want to, every value here should appear. This is an lookup argument. And an indexed lookup argument is when you have an indexed column, let's say a table column, and here let's say 8, 9, 10, 11, and for instance 1, 3, 0, 1, and the result of this lookup argument, the data, let's say 1 here, 9, 3. So 0, 1, 2, 3, 11, 0, 8, 1, 9. Okay? Am I clear? So the data is clear? 3 here, 0, and 1.
This is lookup star.
Yes, but yes.
Yeah.
But more generally, this is an index. You can build it without lookup star. Because
Yeah, we can discuss lookup star later because this is like the end of.
just a conceptual definition, this is an indexed lookup, and Lev used the notation like this. And it turns out that if you have a lookup argument, it's easy to build an index lookup argument. So using lookup, which is the most famous lookup argument currently, you can build an index lookup argument using simply lookup. You don't need lookup star. And so this is an index lookup argument, and in the current proof system, you commit to your memory, which is one long slice, one long slice of field elements in the basis field, and you have your execution table. And in your execution table, you have like 3 indexes. Let's say index 1, index 2, etc. And corresponding to these indexes, you have values. For instance, if index 1 is, let's say, 2, here you want memory at index 2. If it's 3, you want memory at index 3, etc., etc. And this is simply an indexed lookup where I is this column, T is the memory, and you will look up into the memory and obtain the resulting values D here. And using this like just conceptually, it's quite simple. An index lookup where you have a table, some indexes, and the resulting data. And so actually in the current execution table, there are 3 indexes column and 3 resulting data column that will store the values of the memory accessed at the corresponding indexes. And 3 because in our opcodes, add, merge, etc., there is always 3 values, x plus y equals z. And so we need 3 lookups, 3 indexed lookups. And that's it. So in this construction, you don't have a permutation argument where you permutate and you use the round product. Conceptually, what you need is like simply index lookup argument. And
so what are the indices in this context?
sorry.
What are the indices in this context?
The indices is so in the execution table you have one column, actually 3, but let's say one column which will store indexes. And for instance, when you say you want to add memory index fp plus 3 plus memory, let's say, I don't know, anyway, here this will appear in your index column.
So you would assign a number to fp plus 3?
Yes.
Okay.
This will appear in your index column, and there is in proof system there is a lookup, an index lookup that enforces that if fp plus 3 appears here, automatically in the corresponding value column there will be memory indexed at fp plus 3.
So is the number assigned to fp plus 3 the actual physical memory address?
Sorry?
Is the index assigned to fp plus 3, is that the address?
Yes, fp plus 3 is the address. Yes.
Okay, so you would take the current value of fp, you would add 3, and that would be the index.
Yes.
Okay, got it.
Yes, correct. Correct.
I mean, are you using anywhere here multi-set hash function or not?
Sorry?
Are you using anywhere multi-set hash functions?
Yes, but not in this part. At the end, you need to prove consistency between, because there are a bunch of lookups like this, and in the end, you need to prove a global consistency to ensure that the precompiled score, so when you calculate the Poseidon cost, it's it's coherent.
Right.
And in this kind of case, you need some kind of multi-set hash.
But you're not doing with elliptic groups, right? Because the majority of people doing that with elliptic
Like
groups.
okay. In the end, there is a complete argument to prove global consistency in the end, but no.
Why did you decide to not go with the approach of Pharaoh? Because it seems a little bit more complicated.
Yeah, the advantage is that actually it seems like actually lookup star, which will be introduced later, enables to save a lot of commitment cost. Because in lookup star, this column value, this column that contains the indexed data here, this column, you do not commit to it.
Oh, okay.
It's
Now it's
virtual.
working better.
And so there is some pros and cons, but in particular, this was a lookup about the memory, from the execution table in the memory. But there is also a lookup from the execution table into the bytecode, because you want at each cycle to fetch the current instruction, the current opcode. And you can see this as an indexed lookup from the program counter column into the bytecode. Because if the program counter is 11, I want to fetch the instruction at the 11th instruction.
How do you enforce that the FP, that if there the FP plus 3 is actually the correct value?
There are some error constraints in the execution table, and that will tell you if the instruction is add. There is like some, I don't know if you get it,
The code?
the minimal leanVM paper, if you can find it, please. Basically, it's an error constraint.
Okay.
Why do you need to fetch the instruction? Aren't they embedded in the table? Like,
When you need to fetch the instruction?
because like do you put like the decoded instruction on the trace table and
Yes.
it's already there, so you don't need to go to the memory, like it's just
No,
too much.
It's a lookup. For instance, in Cairo, what you would do is that you would commit to something like 15 columns that contain the decomposition
Yeah.
of your instructions.
Yeah.
And you can interpret those 15 columns as an indexed lookup from the program counter into the bytecode. When, like a multi-column indexed lookup. And using lookup star, you can avoid committing to these 15 columns because they become virtual thanks to lookup star. And this is the exact location where lookup star will make you gain a lot, because you will avoid committing to these 15 columns, which is a lot. Like,
Okay.
yeah, in the end, you commit in the current implementation. For each cycle, in the execution table, you commit to 5 columns, which is much less than in Cairo.
So did you say it was the data that's virtual, not the indices?
Exactly. So the table is like the memory, and so that there is a lookup from the execution table to the memory. But in this case, the table is the memory. The index is like FP plus 3, for instance.
So in Cairo,
Sorry, okay.
the flags, those are indices or data?
They are the data, like the result, the lookup from the bytecode. So the index is a PC,
Oh, right, of course, yes. Okay.
and the 15 flags are the result of this lookup.
Right.
One of the criticisms that Jolt mentioned, an advantage of Jolt versus the other CKVM is the number of committed elements compared to other VM. Do you know how much they have? They use?
In short,
Yeah.
I don't know. But what I can currently in this system, we commit at the execution table level. So if I do not consider the memory, there is only 5 field elements committed per cycle.
Can you clarify a little bit more the two lookup arguments, the one for the execution of the memory compared to the execution of the bytecode? Like in the case of the memory, I understand that you have this key column, you know, that you have all the information. But in case of the bytecode, like what do you have that is the equivalent of T?
I will describe precisely the execution table. In detail. There is FP, PC, index 1, index 2. Can you read what I write?
Yep.
Okay. Index 3.
One base index.
Value 1. 1, value okay, value 2, you understand, and value 3, okay. And I continue there, and then, okay, well, I will just write one index and one value, okay?
Okay, sure.
Index 1, 2, and 3, and value 1, in parentheses 2 and 3, okay. And you also have opcode flag 1, opcode flag 2, etc., etc. Let's say 15 or 16 of them that represent, that encode your instruction. And so here is your.
At first, we only add 4 instructions, so one of those flags.
Even though there are 4 instructions to encode to represent the
memory or immediate.
Exactly.
Okay.
Exactly. For instance, and there are also Poseidons, etc. But yes, correct. And the jump, if it's you jump, do you update FP or not?
Yeah. Okay, I see.
And so this is the memory. Okay. Okay. And this is, let's say, the bytecode. Bytecode 2. Okay. Actually, bytecode, I should represent it vertically because there are bytecode like 15 columns, and so this is like the first instruction, then the second instruction, etc., etc. Third instruction, etc. And there are 2 lookups that are very important. First, you want that the value correspond to the index in memory. So these 2 columns here are linked to the memory. That there is an index lookup into the memory. And then there is the flags for the decomposition of your opcode, which is related to the PC column. So PC goes with those opcode flags, and there is an index lookup into the bytecode.
Is that index an address or
Sorry?
the index is an address?
The index is the program counter. At which location are we in the bytecode currently? So for instance, initially the program counter will start at 0, which means that at 0 I should have the first instruction. The first here. So this line here should appear here.
Okay.
Is there is there an advantage to having opcode flags instead of calling them add and add I? For example, for add and add with immediate, jump and call versus ret, because
Yeah, I would say it's equivalent. Yeah.
okay.
Yeah, but indeed, you could have a more granular way of doing it. Yes, it would work. Yes. But actually, the add I and the add not would have quite some part in common in the R constraints. But it's the same in Kero. In Kero, there are a bunch of opcodes, but in practice, you could create new opcodes because there are flags and you can put whatever you want in the flags. So you could create an instruction with a very weird behavior by mixing the flags. Yes. And the key point is that you do not commit. So this value here, you do not commit to it, and this value, these columns, like all the columns that are the result of an indexed lookup argument, are not committed. And this is a topic I would like to discuss to weigh the pros and the cons of lookup star with the lookup on memory. It's an interesting subject, but when it comes to the bytecode, the advantages are absolutely clear because for lookup star is extremely efficient in 2 cases. First, when the table, when the table, in our case, the bytecode is small, which is the case. In practice, the bytecode is small because the execution table think like 1 million cycles, something like this. The bytecode think a few thousand instructions maximum. So, and seconds, multiple columns. In which case, lookup star is also very well suited. So the lookup star lookup is extremely well suited when it comes to the bytecode. When it comes to memory, it depends in some context, and this is an interesting subject. Sometimes it will be slower than classical lookup, sometimes it will be faster. Okay.
Can you show us lookup star?
Yes.
Yeah. So yeah, the basic logger, let us say, the basic logger, like you have this with the product, and with the logger you just take like the derivative with the log, and then you end up with the sum. This sum, you run this sum like line by line, and so at the end you have like the initialization, and then at each line you have this implementation line by line running the sum. And at the end, you just check that your final line is 0 and not 1, as we mentioned previously with the product. That is the lookup. And then there is this lookup star technique. So, as just mentioned by Emil, you have this table T, that is a small table, usually. And you have the index column, E, that is a large column. So it could be quite large, but with element very small in there. And so you just look up the value like this. I have this explanation then there. So this is basically what we are trying to do. So I star T, that is so the index lookup. So you have this table of index and the value that you want to check at this corresponding index. In this case, so you just do that. So basically, if you have a very small table T, 20, 30, 40, and then you have the index, then you just do that so that you go to grab the different index value. If you go to this, you have this, and then I think I have an example of, so for example, if you have this and with all of this index, so you can see that typically this can be big numbers, and this is very small because these are index. And if you had to commit to this multiplication table, this can be, as it is a combination, this is large table with large value inside, so this is very costly to commit to. And so you have this new idea, maybe like this could help you. I think that it will be better to explain it because I explained it, but there is this pull back and push forward. So this is this technique with the sum check in the middle. Here I have some equation. So you have this, you rearrange in some sort with an A, and then you have these sums. And so you compute for each G A multiplied by A, and then the sum over A, the I equal G, where you compute that for each G. This is correct. And so finally, after you have this, so you have this table that seems small, that is the pullback, and then you use this duality lemma, correct?
This is the key thing.
Yeah. So so this is basically an equality that helps you rearrange the term and then end up with the final. So, for example, maybe can you explain us how you implemented this into the code, like this rearrangement of stuff?
Do you want that we take some time in the mathematical details on everything in a star? It's possible, but I know.
I don't understand the explanation, so.
Yeah.
Okay. So notion of pullback. This is the index lookup I presented. You have this. This is the index. So if you access at index I, so index I, this is simply table like this. This is the pullback.
Let us go maybe with some kind of example like this, like the time and T table, like there's much table.
There is another solution. Take. It is a different notion but similar. So I take the sum on E and take. This is the sum on R de. I take the sum on the G such that E of G equals I and then I take
It's equal E equal J.
sorry. In the index, I sum in I take all the take.
I know you inverse it and you said, yeah, this is okay.
Is this,
Yeah, it's okay.
Is this pullback a pullback in the category theory sense?
Yes.
Okay.
It's a pullback and it use pre-composing with a function. It's much simpler. I don't think we need to talk about categories, right?
Okay. And the key point is that, and just for instance, okay. And the key point is this lemma. If you have two tables.
So first, the pullback is that, is it clear for everyone, like if you have like a table T, 10, 20, 30, then you have another table of indices, and then you just go to T of I. So for the first one, for example, it's T of 2, and so this is 30. So you do all of them, each I.
If you rearrange the sum, you can say it's the sum of G, and you take all, you say and then sum G, and then the sum of G, such.
Is the HackMD public or somewhere? No.
Yeah, this is, I think. I can send you the link afterwards.
Yeah, Thomas, if you want to drop your slides and the HackMD to me, I'll
Yeah,
put
yeah,
them all in the YouTube
Yeah, for sure.
comments.
Then you need to write.
Yeah, so I'm going to try to collect all the presentations, the videos, the transcripts, and put it all on the leanEthereum GitHub org so that people can go back to it. And we've got the ones from ECC at Cannes a few months ago too.
Okay, so anyway, don't spend too much on the details.
That's the proof, right? But
Okay,
you just
Okay, just read it because it's simply that there are two sums and you need to switch the indexes. It's not very complicated. Just switch the indexes in the sum, it will work. Okay. And
Famous
okay.
last words.
And using this slide,
Exercise the reader.
yeah, exactly. Actually, what you want to do in practice is to evaluate the column containing the index data at a random point in the extension field. So what you want is to have like the multilinear extension of this thing evaluated at a random point in the extension field. Okay? But this thing can always be understood as an inner product. So with the equality kernel. And here you can use this lemma and switch, and you access this. And here you trade the pullback for the push forward.
Just here, maybe like with a small, just with a small example to show this product stuff. So if we take A, B, and I, if we go to the same steps that I just mentioned before, so you just do B1, so that 20, 10, 20. So then you have this vector of E cross B, and then you do the first side of the multiplication. So you do 2 multiplied by 20 plus 3, 10, and 4, 20. You end up with 150, and then you compute the other way, and you end up with 3, 6, and then you compute like the dot product again, and you see that the 150 that you obtain this by doing this way is exactly the same dot product that you obtain here by doing the other way. That demonstrates kind of an example of this equality.
And this equality, the idea is that you will run a sum check to prove this thing, because it's like an inner product. At the end of the sum check, the verifier will access, so you express it like a sum, E, this, okay. Okay, and at the end of the sum check, the verifier will need to query this multilinear polynomial and this multilinear polynomial to be able to evaluate the expression inside the sum. This thing, the table, has been previously committed or is accessible by the verifier, because T is either the memory or the bytecode. If it's the memory, it has been committed, so the verifier can query T at some random point. If it's the bytecode, the verifier can access by itself by evaluating the bytecode as a multilinear polynomial. This thing is less trivial, so the verifier needs to evaluate the push forward of the equality kernel at R at some random point. Let's say, so the verifier needs to compute this thing at some random point, let's say alpha. And to do this, it's the same trick as in lookup. So you will use a sum of fractions, but here the sum of fractions will be slightly different. It's what you want to prove is the sum of x minus indexes table minus actually I need to, it's quite complicated. I need to okay.
Need a bigger whiteboard.
Okay. Let's say you want to prove, because in lookup you want to prove a pullback. Let's say you want to prove a push forward, so you want to prove this equality. This. Okay. It turns out you can use something very similar to lookup, which is this. You sum around indexes. Okay. 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 This thing is true only when y is indeed the push forward of this expression. And so you evaluate it at a random, like you take a random challenge, and so typically alpha, you will replace its x by alpha, and this whole sum of fractions will be equal with high probability if and only if this thing is indeed pushed forward. So you will need to run something very similar to lookup. We need to compute a sum of fractions. So in the end, the costs are similar to lookup. It's like the algorithm is similar to lookup. And in our case, the A is the equality kernel at the random point R. This is the indexes that we know, and yes. And you need to evaluate it. Okay. And yes. Let me think. Yes. And so, in terms of cost, and I'm sorry, I'm not extremely clear. I'm sorry, but in terms of cost, the main difference with lookup, I think this is maybe the most important thing to speak about. In lookup, you have to commit to 4 things. So you have your indexes, your table, and the corresponding data. In lookup, you commit to indexes, so I. You commit to the table, so T, it's committed. You commit to the data, and you commit to the accumulator, where in for each accessed index in the memory or in the bytecode, like the data you access, you need to tell how much time did you access this data, like the accumulator.
How many times?
Yes, exactly. The accumulator. In lookup star, you don't commit to the resulting data, and you don't commit to the accumulator. But you need to commit to this thing, to this thing. And this thing has it's multilinear, which has the same size memory as the table. So if the table is small, you commit to something small. And that's why we love lookup star when the table is small. The main drawback is that if your table, typically the memory, is in the base field, this thing, unfortunately, is in the extension field. So this is like a pain point, because for the lookup of the memory, you need to commit to something of the same size as the memory, but in the extension field. And this costs quite a lot. So when your table has the same size as your indexes, clearly lookup star is less performant than lookup because of this thing. But in practice, in our case, there are 3 indexes column per cycle. So each cycle fetch 3 data from memory. And you can approximately say that each cycle will use a new cell in memory. So there are approximately as many cells in memory as there are cycles in the execution. So the size of the memory is approximately the number of cycles. And so in our case, if the indexes, if the table has length n, the indexes has length 3n. And so if we count things in lookup, classical lookup, you commit to the indexes, so you commit to 3n. You commit to the table, so n. You commit to the data, so 3n. And you commit to the accumulator, so n. Overall, 8n. Lookup star, you don't commit to data and accumulator, but you still commit to index table, but this you don't commit, but you commit to the push forward of the equality kernel, which is n times the extension degree of the field. Let's say 5n. If you do the sum, 3 plus 1 plus 5, you are at 9n. So in terms of commitment cost, it's a little bit worse than lookup classical. It's not very, so the thing that I want to express is that for the lookup in memory, lookups when there are 3 times more indexes than when the column indexes is 3 times larger than the memory, the commitment cost of lookup star are similar to the commitment cost of lookup normal. And after this, there is the same sum that you need to compute the sum of fractions, and it will be the same in lookup star. So in terms of cost, it's roughly the same. And after this, there is the question on how do you compute this sum. And you can use it, like you can commit to auxiliary columns, and you use as I mentioned, like an R constraints to enforce the fraction and median equals 1 or something. You can also run GKR, it depends. But the point I want to transmit is that as long as there are 3 times more indexes than there are data in indexes, lookup star is almost as good as lookup for the memory, and for the bytecode is it's 10 times better.
Got it.
I'm sorry for the long explanation.
Maybe what we could do is, I have a final example that's everything with the lookup stuff. So maybe we could go to this and then talk about like the pros and cons of everything, because there are a lot of variants, including like the sum chains. There is a lookup plus GKR. There are a lot of stuff. So yeah, as just mentioned, let us talk about a brief example, see how the lookup star work, and then we can finalize with some questions. So let us imagine that we have a table T and high with indexes. So small values but large table, big values but small table. If like you get like the index 0, you have 100, index 1 you have 200, and the index 0 you have 100. Let us suppose that we want to evaluate that as a random point. This one representing on the Boolean aperture. This corresponds to a selection of index 2 because of the index of 0, 0, 0, and then 0, 0, 1, and then 0, 1, 0. The goal is that you don't want to commit, as just mentioned by Emil, into this big table, because in reality this can be really huge and with big values. So again, like the prover did an initial claim, that is that I dot t of 2 equal 100. Then we define an equal R, that is a kernel just defined by, just proposed by Emil there. And so basically this R is saying that it's evaluated to 1 only at 0, 1, 0, and 0 everywhere else. So this is just like a selector. Then we can compute like I.R by the expression with the big sum that was mentioned at the beginning. So for example, if we go to j equals 0, we have the sum, we have I of 0 equals 0, I of 2 equals 0, and I of 1 equals 1. So only I equals 0 as R of 2 equals 1, and so finally this is 1. If you do exactly the same thing for 1, this is of I dot R of 1 equals 0, and just at the end you obtain this final vector of 1, 0. Then you do the magic trick of switching the inner product. So at the beginning you have this, and then you just switch to have this. If we go numerically with the example, you still have like 100 and 200, and you have 1 and 0, so you just do the dot product. So 100 multiplied by 1 and 200 by 0. This matches the claim value. Then you have the sum check coming in. You have to prove that via sum check. And you open the final evaluation thanks to like the verifier, random challenges during the sum check. And the key point to have in mind there is that with all of this, we never committed to this big table, and instead we committed to this one, correct? This is what you explained. That is small value and much smaller. My question there as a follow-up are like, I guess that it has a lot of complexity inside the code, I guess.
Compared to lookup, there is only this initial sum check here. But once you got this sum check, you need to prove the same type of sum of fraction as in lookup. So the only difference, I believe, is this sum check.
So if you just reuse the sum check that you use in the zero check of the PIOP, you just call it there. And I have seen that a bunch of stuff about like lookup and lookup with GKR. A bunch of teams have tried the two and finally end up with simple lookup without GKR. Do you have any maybe opinion on that stuff to add?
Mine is still using lookup with GKR.
Right?
I think so.
I was thinking that they just, because we asked, for example, to Starkware and they tried both lookup and lookup with GKR, and finally they just abandoned the GKR option. This is still in their code but not used, just lookup.
Why did they abandon it?
Because they didn't see any benefits of that, so this is why they just told us in the situation. Yeah.
Wasn't also this security risk with GKR?
Yeah.
The paper from
Yeah. This is also a possibility.
This is the proving false statements paper.
Yes.
Yeah.
That one doesn't really affect log GKR.
Okay.
But that one only affects GKR if you let the prover have like complete control over sort of. I mean, it's a bit like errors are also broken if the prover gets to write down their own error and they have a broken error. Like if I claim this error says the statement's correct and the error's just nonsense, it doesn't.
That's a bit different, but I see the analogy,
yeah.
right? I mean, error is a specification language. Surely you can specify pointless statements.
Yeah.
That's different from saying if you have error is not sound. But the point stands, yeah, I mean, if it's just lookup, it's not, that attack will not be relevant.
You would have a GKR close to the hash function, like a very complex structure in the GKR to be able to act it.
Back I don't know if you can, back when Shahar was there, like some time ago, I remember like his answer was that some things were faster with GKR, but not all of them. I don't think it worked for Poseidon. I think he told me that it was faster for CageJack and that kind of things. I'm not sure.
Okay. When like you said that when Shahar was back then in Starkware, he told you that GKR is faster for some
For some cases, but not for all of them. So it depends on what are you doing. But sadly, I don't remember the full analysis. So it's just a small hint.
Same talking with Bobby, and I think he mentioned that in Maiden it didn't make things like way faster, so it didn't make sense to have something way more complex in their code base. It's way faster.
I would say the answer depends on how fast is your commitment compared to proving like a product. Because if you don't use GKR, you have to commit to auxiliary data. And I guess that if you use a fry with KCAC, glitchhack, it will be extremely fast. But just to give you an example, like two days ago, I was able to gain 50% on performance for proving Poseidon 2 using WIR and so on, simply by going from constraints of degree 3 to degree 9. So increasing a lot the degree of the air constraints. I modified I used the blanket tree utilization,
Yeah.
but I like the initial and final steps. I batch, like instead of doing a cube by cube, I do a cube then recube, and then I commit. And using this, I reduce the number of committed columns, and it turns out it's faster. Like even though it increases the degree of the error, so the zero check is slower, but the PCS is like much faster. So like we gain like maybe 30% of the PCS, and because the PCS is not that fast in our case, because Poseidon, Wheel and so on, compared to Fry and Jack, I think for us committing it may be slower than other projects.
So you remove cells and added higher memory constraints. So why is it faster?
I removed columns from the Poseidon Earth, but I had to increase the degree of the constraint.
Makes sense.
And it made it faster.
Like you can halve the size of the air if you're willing to do degree 9 constraints, because you get to do like sometimes like say cube things, right?
Mm.
And so if your constraints come up to degree 9, you can sort of do 2 rounds at once because you can just do 2 cubes.
Mm. Okay, makes sense.
How many colors can you eliminate by doing that?
I think 64.
Okay.
Before it was 150 or maybe 160, something like this, and going to like 100.
Okay.
Because there are 4 partial wounds at the beginning, 4 partial wounds at the end, and each partial wound you needed to commit it 16. And so if you cut 2 and 2, you gain 2 times 16 plus 2 times 16. So 64.
But then bumping up your degree of the air to 9, doesn't the rest of the system come slower?
Yes, obviously, yes. But
it's
it's slower, but overall you gain because the PCR is faster.
Yeah. So would it be possible to kind of automate and let it run for, I don't know, 3 hours to check what kind of...
The degree 6, 7, yes. It's a good point because it was easy to go to degree 9 using maybe the optimal is degree 7, I don't know, but it's much harder to arithmetize using degree because
Well, you should go to like 3, 9, 27.
yes, obviously, but between 3 and 9, it's less clear how to implement it.
Yeah, I mean, I think for koala bear there wouldn't be much point. I mean, if you pick a different field, like baby bear and you went to degree 7, then obviously you get the advantage of already having you can do everything one round. Yeah, but otherwise, I think for koala, I think you just want to go up in like 1,003.
Yeah, makes sense.
What was the reason you choose koala here?
It's 1 and 3.
Oh yeah,
Was it?
Anyway, so about the log care, if I think I would bet that the log care in our case will be faster, but I am not. I don't know. If I had to bet.
You also recently, I think, implemented something like jagged PCS.
Yes.
Maybe it's a good time, like, to talk about.
Okay.
Very briefly.
Okay.
Because, like, is it something that is in competition with the logger?
No.
That is complementary to
Yes.
the how do you join
it's a very good point. But we want a break before or after this?
Is it time for break?
Yeah, we can leave a break.
Okay, but it's a very interesting